Imagine a wave that's 15 meters tall approaching a ship head-on. The wave hits the bow with millions of tons of force. The ship rises up the face of the wave. The entire front of the ship is tilted upward at an angle exceeding 30 degrees. The bow climbs higher and higher until the ship is tilted so far forward that it seems impossible it will recover. Then the wave passes under the ship. The bow starts to fall. The stern rises. The ship tilts backward with equal ferocity. Now the stern is tilted up at 30 degrees. The ship experiences forces that seem like they should flip it over. Thousands of tons of cargo are pressed against the sides of the ship. The structure experiences stresses that would tear apart a weaker vessel. Yet the ship doesn't capsize. It doesn't roll over. It maintains stability through the entire ordeal. This is extraordinary. How does a ship that's moving through an environment full of forces designed to flip it over manage to stay upright? The answer lies in understanding the physics of ship stability, a science that's been refined over centuries of maritime experience. Today we're exploring the fundamental principles that keep ships stable in the worst conditions nature can throw at them. To understand why ships stay upright, we need to understand the concept of stability. Stability is the tendency of an object to return to its original position after being disturbed. A ball sitting at the bottom of a bowl has stability. If you push the ball, it rolls but then returns to the center. A ball sitting on top of a sphere has instability. If you push it slightly, it falls off and doesn't return. A ship is somewhere between these extremes. A ship has tremendous stability when calm, but if tilted far enough, it can lose stability and capsize. The two fundamental concepts of ship stability are the center of gravity and the center of buoyancy. The center of gravity is the single point where all of the ship's weight can be considered to act. Imagine the entire mass of the ship concentrated at a single point. That's the center of gravity. For a ship in balanced equilibrium, this point is located somewhere along the vertical center line of the ship, typically above the geometric center of the hull. The center of buoyancy is the single point where all of the buoyant force can be considered to act. The buoyant force is the upward pressure from the water. The center of buoyancy is located at the geometric center of the submerged portion of the hull. When the ship is floating upright and motionless, the center of gravity and the center of buoyancy are not at the same location. The center of buoyancy is lower, typically near the keel of the ship. The center of gravity is higher, somewhere in the middle of the ship. This vertical separation creates what's called the righting moment. The righting moment is a rotational force that tries to keep the ship upright. If the ship tilts slightly to one side, the center of gravity and center of buoyancy shift out of alignment. This misalignment creates a couple, a pair of forces that act to rotate the ship back to vertical. The vertical distance between the center of gravity and the center of buoyancy is called the metacentric height. This is the single most important number in ship stability. A large metacentric height means great stability. A small metacentric height means marginal stability. Zero metacentric height means the ship is neutrally stable, like a ball balancing on a table. Negative metacentric height means the ship is unstable and will capsize if tilted even slightly. Ship designers calculate the metacentric height for every possible loading condition. Before a ship departs from port, the crew verifies that the metacentric height is positive and within acceptable limits. Let's think about what happens when a wave tilts the ship. Imagine a wave lifts the starboard side of the ship higher than the port side. The ship heels, rolling to the port side as the starboard side rises. As the ship heels, the buoyant force shifts. The submerged portion of the hull changes shape. The center of buoyancy moves outward, away from the center line. Meanwhile, the center of gravity stays in place. This shift in the center of buoyancy creates a larger separation from the center of gravity. The righting moment increases. The stronger righting moment pushes harder on the tilted ship, fighting the wave and trying to return the ship to vertical. This increase in righting moment is the key to understanding ship stability in waves. As the ship tilts more, the righting moment actually increases. The ship becomes more resistant to further tilting. The stronger the righting moment, the harder it pushes the ship back to vertical. The wave must push harder and harder to tilt the ship further. There's a limit to this process. If the ship is tilted far enough, the center of gravity can move beyond a point of stability. This critical angle is called the angle of vanishing stability. Beyond this angle, the righting moment decreases. The ship becomes less resistant to further tilting. If the ship tilts past this critical angle, it becomes increasingly likely to capsize. The angle of vanishing stability depends on the ship's design. A ship with a large beam, or width, has greater stability. The wider hull means the center of buoyancy moves further away from the center line as the ship heels. This creates a larger righting moment. A ship with a narrow beam has less stability. The geometry of the hull is critical. A ship with a hull that flares outward, becoming wider above the waterline, has better stability than a ship with a hull that curves inward. The flared hull creates more buoyant force at larger heel angles. The height of the center of gravity is also critical. A ship with cargo and machinery positioned high in the hull has a higher center of gravity. This means the metacentric height is smaller. The ship has less stability. This is why ships load heavy cargo low in the hull and light cargo high up. This distribution keeps the center of gravity as low as possible. A ship that's loaded with all heavy cargo on deck and all light cargo in the hold might have negative metacentric height and could capsize in rough seas. The crew and captain must be aware of cargo loading and its effect on ship stability. Free surface effect is another critical factor in stability. When the ship heels, liquid cargo inside tanks shifts. If a tank is partially filled with fuel or water, the liquid surface remains horizontal even as the ship tilts. This means the liquid's center of gravity shifts outward as the ship heels. This shift of the liquid's center of gravity is equivalent to raising the ship's overall center of gravity. Free surface effect reduces the metacentric height. Multiple partially filled tanks create multiple free surface effects. Ships minimize free surface effect by keeping tanks completely full or completely empty. Partly filled tanks are avoided when stability is critical. Watertight compartments also play a role in stability. A ship with multiple watertight compartments can survive flooding in one or more compartments. If the ship collides and one compartment fills with water, the remaining compartments still provide buoyancy. The ship might be floating at a different angle with one compartment flooded, but it remains afloat. The watertight compartments are designed so that no single collision can flood enough compartments to sink the ship. This redundancy is critical for safety. The shape of the underwater hull is optimized for stability. Ship designers use computer models to analyze how different hull shapes affect metacentric height and righting moment across all possible heel angles. The goal is to create a hull shape that has excellent stability without wasting material or reducing cargo capacity. Modern hull designs balance these competing demands. The result is ships that are stable across a range of sea states and loading conditions. Now let's talk about what happens in extreme weather. When a large storm approaches a ship, the sea state changes dramatically. Wave heights increase. Wave periods lengthen. The waves might come from multiple directions. The ship experiences heeling forces not just from the waves themselves, but from the wind that created the waves. Wind can exert tremendous pressure on the sides of the ship. A 100 km/h wind can push on a ship's superstructure with forces exceeding thousands of tons. The ship's motion in heavy seas becomes complex. The ship doesn't just roll side to side. It also pitches forward and back. It rises and falls with the waves. The combination of these motions creates stress on the structure. The cargo experiences accelerations that can cause damage or shifting. The crew experiences motion sickness. But the ship's stability system continues working. The righting moment continues to oppose the forces trying to capsize the ship. As long as the wave forces don't exceed the ship's righting moment at all heel angles, the ship will recover from each wave and return toward vertical. There are situations where a ship can capsize in rough seas. If a wave hits the ship from the side at precisely the wrong moment when the ship is already heeled from a previous wave, the combined effect might exceed the ship's righting moment. This is called synchronous rolling. The wave frequency matches the ship's natural rolling frequency. Each successive wave adds to the ship's rolling motion. The heeling angle increases with each wave. If the heeling angle reaches the angle of vanishing stability, the ship will capsize. Captains and ship designers understand the conditions that cause synchronous rolling. Captains make course adjustments to change the ship's relationship to the waves. By changing course, the captain changes how the ship encounters the waves. The waves that were hitting from the side now hit at an angle. The ship's natural rolling frequency changes. The wave frequency no longer matches the ship's natural frequency. The synchronous rolling stops. The heeling motion decreases. The ship becomes safe again. This simple maneuver, based on understanding the physics of stability, can mean the difference between a safe ship and a capsized wreck. Different ship types have different stability characteristics. Container ships have a relatively high center of gravity because containers are stacked high. The metacentric height is not as large as it could be, but it's sufficient for normal operations. Bulk carrier ships that carry grain or ore have lower centers of gravity and greater stability. Tankers that carry liquid cargo must be careful about free surface effect. Cruise ships have been specifically designed for stability because passengers require comfortable conditions. Modern cruise ships have advanced stabilizer systems that actively reduce rolling motion. The combination of good hull design and active stabilizers makes cruise ships remarkably stable platforms. Fishing vessels and small ships face different stability challenges. A small fishing vessel might have a relatively small metacentric height. The crew must be careful about how they load the boat and distribute the weight. A small boat that's loaded unevenly or with cargo stacked too high might have poor stability. Many fishing vessel accidents are caused by insufficient stability, leading to capsizing. Training programs emphasize the importance of understanding and maintaining stability. Naval vessels have special stability considerations. Warships carry weapons and equipment positioned high on the deck. Gun turrets, radar systems, and missile systems add weight far above the waterline. This raises the center of gravity. Naval architects compensate by using specially designed hulls with large beam and flared sides. Modern naval vessels also use ballast systems to adjust stability as different weapons and equipment are loaded or unloaded. The stability must remain adequate even with various equipment configurations. The stability of a ship can be measured and calculated before the ship ever goes to sea. Naval architects create detailed stability curves that show the righting moment at every heel angle from 0 to 180 degrees. The ship is tilted in a test called an inclining experiment. The test measures the actual center of gravity and confirms the calculated metacentric height. These measurements are crucial. They verify that the ship will perform as designed. If the measured stability doesn't match the calculated stability, the issue must be investigated and corrected before the ship departs on its first voyage. Throughout the ship's operational life, stability must be verified. The crew maintains a stability manual that lists all of the loading conditions and their effects on metacentric height. Before departing port with cargo, the crew calculates whether the loading will result in adequate stability. If the loading would result in negative metacentric height or marginal stability, the cargo must be rearranged. The crew might refuse to depart if stability cannot be assured. This responsibility is taken seriously because improper loading has led to capsizing and loss of life. The role of stability in preventing capsizing is understood through analyzing real accidents. The MS Herald of Free Enterprise capsized in 1987 because a bow door was left open. Water flooded the forward compartment, raising the ship's center of gravity. The metacentric height became negative. The ship rolled in moderate seas and capsized. The ship was only tilted about 30 degrees when it became unstable. 187 people died. This tragedy led to improved regulations requiring ships to be designed so they remain stable even with one compartment flooded. Another famous case was the Vasa, a Swedish warship built in 1628. The Vasa was decorated with sculptures and weapons positioned high on the deck. The center of gravity was too high. The metacentric height was negative or nearly zero. The ship was unstable. On its maiden voyage in calm water, a gentle breeze heeled the ship. Water entered the gun ports. More water flooded in. The ship sank in Stockholm Harbor. The Vasa remained sunken for 333 years until it was raised and preserved as a museum ship. The Vasa's instability was a direct result of poor understanding of stability principles. Modern ships benefit from the hard-learned lessons of such disasters. The future of ship stability will involve more sophisticated monitoring and control systems. Sensors throughout the ship will continuously measure the ship's motion, the position of cargo, fuel levels, and water in various tanks. Advanced computer systems will calculate the current metacentric height in real time. If the stability degrades due to cargo shifting or fuel consumption, alarms will alert the crew. Automatic ballast systems might adjust water levels in ballast tanks to maintain optimal stability. Some experimental ships use active control systems that can adjust the ship's heel even in rough seas. Artificial intelligence systems trained on data from thousands of ships will predict how specific loading conditions will affect stability in various sea states. These systems can recommend optimal cargo arrangements to maintain stability. The AI can predict which routes or course changes will minimize stability problems in rough seas. These advanced systems will make shipping safer and more efficient by optimizing stability based on real-time data and forecasted conditions. The physics of ship stability reveals why certain designs work and others fail. It explains why wide-beam ships are more stable than narrow ships. It explains why high centers of gravity are problematic. It explains why partially filled tanks reduce stability. Understanding these principles allows designers to create ships that are stable across a range of conditions. Understanding these principles also reveals why certain operational decisions, like improper cargo loading or failing to take course adjustments in rough seas, can lead to capsizing. The physics of stability is fundamental to maritime safety. The next time you see a ship in rough seas, imagine the righting moment working to keep the ship upright. Picture the center of buoyancy shifting as the ship heels, creating the counterforce that resists capsizing. Visualize the crew making course adjustments to avoid synchronous rolling. Understand that the ship's stability is the result of careful design, precise calculation, and operational procedures developed through centuries of maritime experience. The ship might appear to be at the mercy of the waves, but it's actually equipped with the physics and design to survive even extreme conditions. If you're fascinated by the physics of ship design and how engineering principles determine whether ships survive or sink, subscribe to the channel. We regularly explore the systems and principles that make maritime engineering safe and effective. From buoyancy to stability to structural strength, each principle reflects decades of research and real-world experience. Understanding these principles reveals how physics applies to practical challenges. Your subscription supports the creation of content that reveals the hidden physics behind the structures that shape our world. Thank you for watching and for your interest in understanding how ships remain stable and safe even in the most challenging conditions.